All right, so the next chapter we're going to cover in the Klein textbook is all about addition reactions. So make sure, depending on the addition you have, you're looking at the chapter that covers addition reactions of alkenes. So let's talk about what an addition reaction is first. An addition reaction is like elimination, but in reverse. So let's kind of do a little bit of review of what we finished up with last chapter. So in an elimination reaction, we needed two different things as our starting materials. What was one thing we needed for an elimination reaction? Either E1 or E2. What do we need? So close, we need a base, right? So elimination, we need a base. With substitution, we would need a nucleophile. So similar ideas. Some bases are good nucleophiles. So what I would say is we need some sort of base. So I'll just call this B with a negative charge and a lone pair. That will be our base. What else do we need to do an elimination reaction? We need our substrate. And what's special on our substrate? It needs a good leaving group, right? So typically in an elimination reaction, you have something that looks like this with a leaving group. I'll just write Lg. And what sort of protons do we go after with an elimination reaction? Beta protons. And if you remember, the alpha position is the position with our leaving group. Beta is one away. So in this molecule, we've got beta protons over here. We also have beta protons on the other side. Does it really matter which side we go after? No, it gives you the same product. So in this case, our base will go after one of these. It's important to remember that it should be anticoplanar. So if we want to, we could even show this trying to go after an anticoplanar beta proton. Clamp down, kick off our leaving group. We get our conjugate acid out, and then we would get an alkene. And our leaving group would be a negative charge. So really the big transformational difference here is we went from an alkane that had a leaving group off of it to an alkene. So we saw how to make alkenes last chapter. Addition is similar. In an addition reaction, it's kind of the opposite. What we do is we start with an alkene. It could be a wide variety of alkenes. And then you treat it with some sort of new electrophile, which I'm just going to abbreviate as X and Y. And when this happens, you can get X and Y to basically add to the positions where the double bonded carbons were. So X and Y will now be covalently bonded to the carbons that were formerly a part of that alkene. So in this situation, what we're doing is we're going from an alkene to an alkane. All right, so now abstract question. Entropically, which one's more favorable? So which one's favored based on entropy? And how do we determine whether or not something's favored by entropy? So entropy favors disorder, right? So in this case, which one's giving us more disorder? Elimination. So elimination is entropically favored. Does that mean we want to run it at high temperatures or low temperatures? What favors disorder, hot or cold? Hot, right? So up here we could say that this is typically favored under high temp. Where if we think about the bottom reaction, is high temperature going to be favorable? Is it going to help us out? No. So in this case, these are typically done at low or moderate temps because we don't want to increase disorder with addition reactions. In fact, we want the system to become more ordered. We're going from 2 moles of starting materials to 1 mole of reagent. So it's a little bit different here. So we have to think about disorder. All right. Now I did want to make an important note here. Last chapter, or even before that, we talked about nucleophiles a lot, right? What makes a good nucleophile? Something that's not bulky. So a nucleophile is something that is, and then I'll do ... I heard somebody say not bulky. What's another characteristic of a nucleophile? Negative charge. Typically, this is also seen by having a lone pair, right? That negative charge makes it intrinsically unstable. It wants to find an electrophile to react with. What else? There was one other thing we didn't really talk about in terms of nucleophiles last term. Unstable. I would say unstable is still kind of correlated with the negative charge. There was one other class of nucleophiles we just never worked with. We talked about double bonds, right? How many of you remember me putting down double bonds as a nucleophile? It was briefly mentioned, right? So this is going to be kind of the key feature of this chapter, is we're going to be looking at double bonds acting as nucleophiles. Really, the key feature for a nucleophile is it is a molecule with high electron density. So it could be a negative charge, it could be a lone pair, or it could be a double bond. Any one of those has high electron density. So in this case, the double bond has high electron density in what sort of orbitals? It'd be the p orbitals, right? So the p orbital sticking kind of up and down through a central atom, those orbitals, when they form that pi bond, can act as nucleophiles. So that's going to be the key feature of these addition reactions. In this case, this double bond is going to be our nucleophile. And what do you think this must be then? If it's not a nucleophile, it must be an electrophile, right? So this other component must be the electrophile in the reaction. So this would be our nucleophile, and this would be our electrophile. All right, so let's take a look at the first reaction. The first reaction I like because it's fairly intuitive. And in this reaction, we're actually going to use the alkene that we were previously looking at. And for our electrophile, we're going to use HBr. So previously we said that this must be our nucleophile because it has a double bond, and this must be our electrophile. And we know that nucleophiles like to attack electrophiles, right? So now my question for you is, what makes more sense? Would it make more sense for us to attack the hydrogen, or does it make more sense to attack the bromine? Check with your neighbor and see if you can agree. Which side are we going to attack? All right, raise your hand if you think the hydrogen. Raise your hand if you think the bromine. So it looks a little mixed. All right, let's ask ourselves, what makes an electrophile an electrophile? Is it electron rich or electron poor? Okay, it must be poor, right? And over here we said a nucleophile must be electron rich, meaning it has a lone pair, a negative charge, or a pi bond, right? All right, so now my question is, all right, which side of the electrophile is more electron poor? And why? The hydrogen. If we think about it, right, we've got a net dipole because the bromine's more electronegative. So the hydrogen side of hydrobromic acid is more electron poor than the bromine side. If anything, the bromine side is electron rich. So it's not very electrophilic compared to the hydrogen. All right, so now when we do this, we can't have two bonds to a hydrogen. So we must have to kick off bromine, almost like kicking off a leaving group, right? Because bromine we know is stable when it gets kicked off on its own. All right, so now we've got a few questions to deal with. All right, the double bond is the thing attacking. So the question I have is, the hydrogen going to go off the central part, or is the hydrogen going to go off the left-hand side? What makes more sense? So which one is more likely to be favored? Let me rephrase this. Which carbocation is more stable? First one or second one? Second one, why? Secondary carbocation, right? So over here, we've got a primary carbocation, which we know is less stable than a secondary carbocation. Therefore, experimentally, we never get the less stable carbocation. It always prefers to go to the more stable intermediate. So that's not observed. And then, like we saw, bromine, in this case, was kicked off as a leaving group, so it's kind of floating around, just kind of hanging out in space right now. Yep? So you're thinking about which one's a better leaving group, hydrogen or bromine? I suppose you could use that as an explanation for why the hydrogen's the group that it's attached, but really it's more the fact that it's really electron deficient. Yeah, good question. All right, so in this next step, what do you think that bromine could do? It's a weak nucleophile. We got a carbocation. Looks a lot like an SN1 reaction, right? In SN1 reactions, we said weak nucleophiles will add into carbocations, no problem. So in this reaction, we've added hydrogen and bromine across that double bond. So this would be our product. All right, so let's make some notes. First one is always form the most stable carbocation. What's something we have to watch out for with carbocations? Yeah, so watch out for rearrangements. So that's first one. And then second thing is, this is called Markovnikov addition. So anytime you see the term Markovnikov addition floating around, that means you're going through a mechanistic pathway where you're forming the most stable carbocation in your addition reaction. It makes a lot of intuitive sense why he got credit for it. It's beyond me. It's just kind of the traditional way these reactions are done. And another way of describing this that makes it a little bit easier is this just means that the halogen adds to the more substituted carbon. All right. There's one other thing I really want to point out, and that is to watch out for stereoisomers. And let's take an example of this. All right, so in this example, we're going to use a more complicated alkene. Let's do this one. And I've got hydrobromic acid. And in this reaction, the double bond, like we said, can reach out, grab that electron deficient hydrogen, or in this case proton, and kick off bromine or bromide as our leaving group. All right, my question for you is, where would the positive charge prefer to be? At the green position or the red position? Red one, why? More stable. So like I said, Markovnikov addition implies that we always want to form the more stable carbocation. All right, so in this situation, we now have bromide. And bromide, we said, is a weak nucleophile. It likes to add into carbocations. And if we think about this, it can add into the carbocation through the top or the bottom. Why? Does anybody remember? So let's go back. What's the hybridization of this central carbon? It's sp2, right? So if it's sp2, what's the geometry? It's trigonal planar, right? So over here we'd say sp2, meaning it's trigonal planar. So this bromide really has no preference for attacking the top face or the bottom face. It can attack either side. And we'll see why that matters here in a second. So let's do both. So imagine over here, we do the top face attack. That means that the bromine must be installed as a wedge. What about the methyl group? So what I mean by the methyl group is what happens to this methyl group that I've circled? Would it be a straight line? No, it must be a dash, right? Because we're forming a tetrahedral carbon that's now sp3. Okay? If we do the bottom side attack, then the bromine would be a dash. All right, what's the relationship between these two products? How are these related to one another? They're enantiomers, right? So you do have to watch out for forming mixtures of enantiomers. All right, let me go back up to the previous problem, though. Because in the previous problem, we didn't worry about forming enantiomers. Now we'll ask ourselves why. Why didn't I worry about enantiomers in this reaction? There's no stereocenters. So how can we have enantiomers if we have no stereocenters? In that case, it's just nice and easy. A lot of students get confused and they're saying, well, why isn't that a stereocenter? We don't have 4 different groups coming off of that carbon, right? So in this case, it's not a stereocenter. We don't need to worry about stereoisomers in this situation. So that's one key thing you have to watch out for. I did want to make another note too. So my other note, so we got kind of 3 bullet points. One is always form the most stable carbocation. Watch out for rearrangements. Second is this is called Markovnikov addition. And third is this works with HBr, that's the most common. It works with HCl and HI. Doesn't really work with HF very well, ironically. Yeah, so let's think about this. In bond line structure here, do we have to show the bond to hydrogen? No, so let's clean that up. Now let's look at it. If we look at this central carbon right here, it has 2 different methyl groups coming off, therefore it's not a stereocenter. Great question though. All right, so let me just put that in there. I like to keep track of where both new groups were added on though, so just for practice, I'll show them in there. Does that make sense? All right. So now, what I wanted to do, I think we'll have enough time, is kind of clarify this Markovnikov addition. All right, for this one, we're not going to worry about the mechanism because we've already done it. We said with Markovnikov addition, the bromine atom ends up on the more or less substituted carbon atom? More. So in this reaction, we said that the bromine ends up on the more substituted reaction, and we said that this is Markovnikov. And I'll just abbreviate this to make life easier. The interesting thing with this was in the late 1800s, when chemists were working on this, once in a while, they would get this product where the bromine would actually, let me actually put it on the other side, just be consistent. Sorry. Bromine would sometimes end up on the less substituted carbon, and this was called Anti-Markovnikov. This was pretty weird, and what they were finding was that they were not getting reliable results. A chemist in the United States might only get Markovnikov addition, or a chemist in Russia might get Anti-Markovnikov addition. And it took a lot of careful research to figure out what in the heck was going on. What they found out was that Anti-Markovnikov addition was actually due to an impurity in their reagent. And it's a pretty cool impurity that was an accident. And I call it ROOR. It's an alkyl peroxide. So when I write R, R is just short for some sort of alkane or alkyl group. But what they found is in some portions of the world, they couldn't get their hands on a pure supply of HBr. It was actually contaminated with these peroxides. And when these peroxides were present, you actually get the bromine to add to the less substituted carbon. So I'm going to make a note. We do want to know what anti-Markovnikov addition is, but we don't need to know this mechanism yet. We're going to cover this mechanism when we get into radical chemistry, but it's a pretty interesting mechanism. However, in the Klein textbook, he shows it in this chapter, so I just wanted to briefly introduce it, saying that if you have peroxide, it actually flips the bromine to the less substituted carbon rather than the more substituted carbon. Do you think this goes through a carbocation intermediate? No, it actually goes through a completely different mechanism that doesn't involve carbocations, and that's why the bromine goes to the less substituted side. All right, so now let's kind of jump to a different one. Next one's halogenation, but it's a little bit different. We're going to start out with an experimental observation, meaning we're not going to focus on the mechanism right now. We're just going to say, if I put these things in, what do I get out? So the experiment that we can imagine running involves a cyclohexene, specifically 1-methyl cyclohexene. Instead of reacting it with HBr, though, we're going to react it with Br, so elemental bromine. And what these chemists found was when they mixed these together, they got the following products. They got both bromines to add across the double bond. What do we notice about the relationship of the bromines? They're anti, right? They're on opposite faces of one another, right? So that's kind of unique. So they're anti to one another. However, who's to say that that top bromine's a wedge? Maybe that top bromine could have been a dash. What must the bottom bromine be if the top one's a dash? A wedge. So what they noticed was that they got anti-addition of bromine. So that was kind of unique. What's the relationship between these two molecules that we got out, though? Are they the same? Not quite. How are they related? They're enantiomers. And in this case, they got a mix of enantiomers. So pretty unique experimental observation. What would the optical rotation be for this mixture? 0. So that was how they checked it. They just did a simple optical rotation check. They saw it was 0, but they knew it was anti-addition. So now the question is, well, how does this mechanism work? So let's take a look at the mechanism. And let's try option 1. So what chemists like to do is first run the experiment, see what they get out at the end of the experiment, and then propose some mechanisms. So that's what we're going to do in class. All right, so let's do option 1. And we'll just, as scientists, propose our own mechanism for this reaction. So what I see a lot of students do when they're proposing a mechanism for this reaction is they say, okay, great. It looks a lot like our previous reaction. Maybe it's grabbing this bromine and then kicking this bromine off. And if that's the case, kind of like with the previous one, we'd want our positive charge to be on the more substituted carbon, right? Which means the bromine must have been installed kind of down here. So a lot of students look at this and they say, well, this must be a lot like halogenation, right? Where we want to get our more stable carbocation. All right? The other tricky thing is we have a stereocenter here, right? So who's to say that that bromine's a wedge or a dash? We might get either. So let's keep that into account as well. So let's say we get a 50-50 mix of bromine here. Plus bromine as a dash. So we've got a mixture of enantiomers right now. And then we've got bromine in either case kind of floating around as a negative charge. So just like we saw in the halogenation reaction, I see this often where students will say, well, maybe it could do a top side attack, or maybe it could do a bottom side attack. If it does a top side attack, then the bromine must be a wedge, methyl group a dash. Does that make sense? And then let's do the bottom side attack. If that happens, then the bromine would be a dash on the top. So let me slide this over just so we have enough room. Do we agree on those two products, at least based on this proposed mechanism? We don't know if it's right yet. We're just proposing it. Right? Same thing with this other one. You could say, well, it could do either a top or bottom side attack there. So I see this every year where students say, well, this looks like the halogenation reaction we just covered, so shouldn't we get 4 different products out? Does anybody see a problem, though? What do you see? With your third one, I think you have an extra bromine on there. Well, that's a big problem. Thank you. That was the problem that I saw. That is a big problem. So, A, I had a typo. What else? Let's think back to our experimental data. Did we have 4 products in our experimental data? No. So problem, experimental data says only 2 products. What else? The ones that aren't products have the bromines on the same plane. Ah, yes. So Kyle was basically saying up here, we said that we observed anti-addition of those bromines, meaning one must be a wedge while the other's a dash, right? Meaning opposite faces. Same thing over here. We've got a dash and we've got a wedge. So let's cross out the ones that must not make sense. So which ones don't make sense? Well, these are both wedges. That's not observed. If we go over here, these are both dashes. That's not observed. Does that tell us that this mechanism is correct? No. So we've got 2 problems. All right, so option 1 is wrong. All right, this is honestly how organic chemists go about solving these mechanisms. Is they come up with something, they look at their experimental results and they say, all right, does my proposed mechanism match my experimental results? If yes, maybe I'm right. If no, I'm definitely wrong. So this is what they found, and they said, well, it can't go through a carbocation intermediate. So let's take a look at option 2. All right, so the option 2 gets a little bit more elaborate, and that's kind of where we'll end off today. So option 2 says, well, maybe it does something a little bit more funky. Maybe the double bond attacks bromine, but then bromine immediately attacks back in. So you've got this almost circular attack system. And then we kick off bromine as our leaving group. All right, so if that happens, bromine actually forms this 3-membered ring. And in this case, bromine could either be attached via wedges, like I have shown, or alternatively, bromine could be attached via dashes, right? So the question is, why might this be observed? Well, let's think about this. Let's consider the reaction that we had shown previously. Over here, we said, all right, we proposed originally that there was a carbocation right there. Bromine is a pretty big atom, and it's got these lone pairs over there. So instead of this happening all at once, this will attack immediately back into that carbocation because it's so close and so big and so electron rich, it just kind of falls over into that carbocation and doesn't allow it to be formed. Does that make sense? So really, this is one way of kind of viewing it, is this is more of a transition state where we're forming this three-membered ring bridge. That bromine's essentially falling into the carbocation. All right? And then in the last step, it's kind of neat. If we think about bromine with a positive charge, is it happy? No. Bromine does not like having a positive charge. If anything, bromine wants a negative charge, right? Being a halogen. So it's going to hog a huge amount of electron density away from this carbon over here. And we know that this carbon that's more substituted is actually okay with a partial positive because it's highly substituted, right? And then bromide will do an SN2 reaction. Attack that carbon and slingshot open this bromine as a leaving group. Just like we saw with SN2 chemistry. What was one of the key features with SN2 chemistry? We only get one product. What else?
Something with stereochemistry.
So normally we don't see SN2 chemistry with something that's sterically hindered. In this case, it's actually allowed because our leaving group is so ridiculously unstable. The bromide, or bromine in this case, just wants to leave. What about the stereochemistry? Do you remember stereochemistry from SN2? It'll invert, right? So do you remember that flipping inside out effect for SN2 reactions? The same thing is proposed here in this mechanism. So if we think about this, the bromine that gets shot open in this one is still going to be a wedge. We didn't change that stereocenter. But the bromine that did the backside attack must be a dash, which means that the attached methyl group must be a wedge. If we look down here, kind of same idea. The bromine that was slingshotted open would still be attached via a dash. The bromine that attached in this case, must be a wedge. And this must be a dash. So the question is this mechanism supported by experimental data? Yeah. Yes, we're only getting two products. Second question is, are we 100% absolutely confident that this is the only mechanism? No, but it seems to make the most sense, so we're going to run with it. That's how organic chemistry works. We propose mechanisms, we cross out the ones that couldn't possibly make sense. The mechanisms that are plausible are the ones that we run with. It doesn't mean that they're always right, but it seems to make the most sense, and they're the way we solve, or at least propose mechanisms in organic chemistry. All right, so that's where I'll end today.